Today what we're going to do is learn how to work with birthday balloons, something that you would blow up for a birthday party, and we'll learn how to put these balloons directly into a candle flame and have them not pop, have them not melt and pop the balloon. So it's very impressive, it's very easy to do, and we'll learn the science behind what makes this happen. Now we will have a candle in this experiment, so you need to make sure and get permission to do this experiment, get some help, and always have your safety glasses, which I have here. So we'll put those on and we'll go over what we need for this guy. All you need for this experiment is a candle. A very small candle will do fine. You'll need a cup of water. You will need a couple of regular old birthday balloons. I have 2 of them here, and we'll show you why I have 2 of them in just a second. And you can tie these balloons, you know, with your fingers, or if you're lazy like me, you can use paper clips to hold the ends of the balloons closed. All right, so what we'll do is go ahead and get set up here. We'll put the water to the side, put the balloons to the side. We'll put the candle front and center, and we will light the candle. So let me go ahead and do that first. All right, so it just takes a second to go ahead and light the candle. Candle's lit. And the next thing we're going to do is we'll show you what happens to a regular old balloon whenever you put it in here. What do you think is going to happen? Well, if I blow this up and I put it on top of that candle flame, the hot air is going to go. It's going to hit that. Rubber. It's going to melt it, little hole, and then pop. The balloon goes pop. So let's go and check that out. Let me go and blow this up. All right, so there we go. So I'm going to blow it up. Now you can tie it if you're really good at tying balloons. Tying balloons can be difficult, so if you want, you can just, once you get it blown up, you can just twist it a few times like this. So I've got a nice little twist at the end, and then grab one of my paper clips there and just put it right on top of that guy. And if you've done it, you know, nicely, you should be able to hold the end of it and just kind of keep it closed, and that paper clip should keep it closed. All right, so what do you think is going to happen? If I put this guy right on top of this candle flame, it should pop, right? So let's check that out. So we'll put it there. Let's see how close we can get before it goes pop. A little bit down, and there it goes. It goes pop. So we were just a few inches away from that balloon. That's why it's important to wear your safety goggles too anytime you have something kind of popping like that. So the candle flame put heat into the air. It didn't even touch the flame. The heat that was coming up off the candle flame went directly to the rubber, made a tiny small hole in that rubber because it melted it, and then as soon as it made a small tiny hole, the whole thing just kind of pops, right? So that's what we kind of expect. So let's go and relight the candle. It looks like our balloon actually put out our candle flame. Now, the second time we do it, that's why we have 2 balloons. First time we show you what it looks like regular. Now, I want to do the same thing again, but now what we're going to do is put a little bit of water in our balloon. We're not going to fill this balloon with water. We're going to put a little bit of water in it, maybe even less than half a cup of water. So what I'm going to do is just pour a little bit of water into the bottom. So now I have a little bit of water. I'm going to put a little bit more. I would guess, well, maybe that's like probably 4 or 5 tablespoons of water really is all it is. Okay? So we're not filling up the water, we're just putting a little bit of water in the bottom of the balloon. Now let me go ahead and blow it up again. Now we're going to go and twist this guy up, just like we did the last time, nothing different. And we'll put that paper clip on there to hold it there. Now what we have is a balloon, and if we've done it all correctly, we should have water sloshing around the bottom of this balloon. Now, before we do the second part where we put the balloon on top, I'm going to put my candle on a little plate. The balloon shouldn't pop, but just in case it does, we want to have a little plate there to try to catch at least some of the water. So what you want to do is you want to put, you know you have the water in the bottom of the balloon, and you want to put it right on top, the same place we had before, and let's go ahead and give it a good count to 5 and see if we can get this balloon to last. So let's go down. 1, 2, 3, 4, 5. Now if you put your hand to the bottom, it does feel a little bit warm, but it's not super hot. Why do you think that is? It's because you have water inside of it. So what's happening is the heat from the candle is going into the rubber, and normally it would pop that rubber, but since there's water in it, water is a great absorber of heat, so to speak. So what happens is you put the heat into the rubber, the water is sitting right behind the rubber on the other side. It's absorbing all that heat, so it's kind of pulling it in. It loves to take in that heat, and water can absorb a lot of heat, you know, by itself. So it kind of takes the heat away from the rubber, and that kind of prevents it from popping. So let's go ahead and try it one more time and put it even closer. We'll go even a little bit lower. Right on top. And you can see that definitely it would have popped by now. And put your hand on the bottom, not too warm. And so for our grand finale, what we'll do is we'll put the balloon directly on top of the glass and see if by putting it right on top of the glass we can actually smother the candle. So that'll be sort of the grand finale. All right, and so we'll just put it right down there. And the candle is out. So that is a good experiment in basically heat conduction. We did the empty balloon, and that showed us that if you have an empty balloon, you put it on top of a candle flame, it's definitely going to pop, and the reason it pops is because the hot air that's coming off of the candle basically melts a small tiny hole in the balloon, and then it pops. And it really, the other balloon, I mean, it was very, very, very close to the actual candle, but it wasn't even touching the candle before it popped. In this case, what we did is we take the full balloon and we put some water in it, and then the heat goes from the candle into the balloon, and then it goes into the water that's sitting right on the other side of the balloon. That water is pulling that heat, conducting that heat away from the rubber. So the bottom line is the rubber is not able to get that hot, because as soon as it does get a little bit hot, the water sucks that heat away. So that's what causes the rubber not to melt and not to pop. And you know, we have a bonus science experiment here. What we did is we kind of put the balloon directly on top of the candle, right, to smother it, just to show you how close we could get to it. And look what happens now. If we lift this balloon, try to lift it off, we can actually lift the candle. Now, why do you think that's the case? It's sort of a bonus science experiment. What happens is the air that's directly around that candle down where the flame is very, very hot, right? So we put the balloon on top. Now, before we put the balloon on top, the air is being pushed away from that candle flame. What happens to things when they get hot? The air wants to expand. When things get hot, like air, it tries to go and push farther out and expand. When things get cooler, they try to contract. So since this candle is hot, the air around that candle, when it was burning, is being pushed away because it's all trying to expand because it's getting hot. Now, as soon as we put the balloon on top, we smother the candle. There's no more heat. The air that's trapped in between the balloon and the candle starts to cool down. So it was being pushed away when the candle was on, but once the candle was extinguished, that air that's trapped in there tries to contract and get smaller. And when things get contract, it makes low pressure. So there's atmospheric pressure out here pushing on everything, and inside between the balloon and the candle is a little pocket of air. Since it's trapped, and since it cooled down, it actually has low pressure. So you have low pressure, which means low pushing, inside of here. You have outside air pressure pushing on it. So what's really happening here is the outside air pressure, the atmospheric pressure, is holding these things together. We have air pressure pushing up on the bottom and pushing on the balloon, holding it together. We have low pressure on the inside. It's not able to fight it. So the outside air pressure wins, and it holds everything together. The only way to get these things off is to kind of pop it off like that. I'm Jason with scienceandmath.com. I hope you've enjoyed this experiment. Go get yourself the materials needed. Very simple to find things. Candle, couple balloons, couple paper clips if you want, goggles, of course, and most importantly, adult supervision. Go try it for yourself. Go explore heat conduction and show yourself how you can actually take a regular old balloon from a birthday party, put it right on top of a candle flame, and it will not pop. Learn anything at mathandscience.com. In today's experiment, we're going to make what we call a density tower, or a tower of density. And what that means is we're going to take various liquids that you probably have around the house or that you can easily find at the grocery store, And we're going to put them in a container and watch that each of these layers are going to basically float on top of the layer below it and make a nice colorful tower that we can then use to kind of talk about things like density and buoyancy and floating in terms of what it means in science. So let's go ahead and do that. What you need for this experiment is, like I said, things that you'll probably have around your house. Get some vegetable oil, canola oil, corn oil works fine. You will need a glass of some kind. In this case, I've got a glass jar, but a regular old glass will work fine. I've got some rubbing alcohol here. It's just regular rubbing alcohol that you get from the drugstore. Some water. I've got some Karo syrup here that you can get from the grocery store. Some regular old honey, again, just from the grocery store. Some red food coloring, and in here is just various different things that you find around the house. We're going to try to float and sink these things. I've got a dye here. I've got a pecan here, I've got a rock, I've got a few things in there. So this is sort of like whatever you can find around the house. So all of these liquids that we've listed here, they all have different densities. And density basically lets you know if something is going to float or sink. So if we're talking about water, which is usually, we talk about floating, we're thinking usually in terms of water. If something floats or sinks in water, all depends on its density, the material's density compared to the density of water. And in layman's terms, that basically means, is it heavier than water or is it lighter than water? So when we're talking about if a rock is going to float or not in terms of water, we're talking about how heavy is that rock compared to the same amount of water. If it's heavier than the equivalent amount of water that the rock occupies, then it's going to sink. If it's a piece of styrofoam, for instance, we know that that floats in water, then if the weight of that styrofoam is less than the same amount or same volume of water that it occupies, if it's lighter, then it's going to go ahead and float to the top. So that's what we talk about in terms of water, but that idea extends to any liquid, whether it's canola oil or honey or Karo syrup or whatever. So we're going to explore that here. Let me kind of move most of my materials over to the right-hand side, and we're going to we always do this. We wear our safety glasses and we're going to be safe about things. And what we're going to do before we do anything first is we're going to put our plate here that we're going to work on, because we're going to be dealing with liquids, so we just want to make sure we have something just to catch any spills. Now, one of the liquids here, notice some of these liquids are clear and some of them aren't. For instance, rubbing alcohol. It looks a lot like water, but you know it's not water, it's alcohol. So we want to make it visible. We want to be able to see it if it floats or sinks. So what we're going to do before I do anything else is just put some alcohol into the cup here. And I'm going to put some red food coloring in it. The only reason I'm putting the food coloring in the alcohol is just so we can see it. So we'll go ahead and be generous. We want it to show up. So we'll put, probably 3 or 4 drops, something of that nature on top of, on there. And we'll just kind of stir it up. So now we have a nice crimson color there. So this is not Kool-Aid though, this is alcohol. And we'll see how that reacts, or if it floats or if it sinks on top of the other liquid layers. Now, of everything here, honey actually is the most dense. And that means that once everything is all said and done, honey is going to be at the very bottom. And you kind of think about it, if you've ever held a jug of honey and even compared it to like a jug of water of the same size, the honey is heavier. So that's actually going to go on the bottom. So what you want to do is literally just squeeze it on in there. And the thickness of your layers really is up to you. It doesn't really matter. But you want to have them thick enough so that you can see the end result. Something like that. You can see very clearly that you've got a nice layer of honey there, maybe a little bit more, because this is the bottom layer and I want to make sure you can see everything. So we'll go a little bit more and give ourselves some honey. Now, of everything else we have, the next lower density substance that we have is actually this Karo syrup. It kind of has the consistency of honey. It's kind of thick, like you can see it kind of coating the jar here as I slosh it around. And as things go, if you were to measure the density of this, the highest density would be the honey, the next guy on the list would be the Karo syrup. Now when you're putting the next layers on, you need to kind of do it carefully. Don't just dump it in there super fast, because even though everything's going to balance out in the end and start floating appropriately, if you kind of do it too fast, you might wait a long time for it to settle. So for the Karo syrup, we want to go ahead and just very gently and gingerly kind of add that in. there. So you can see it's kind of clear, and it just goes in, and you'll start to see it float on top of the honey layer. Now you have to look carefully though, because the honey is already kind of transparent. It's got an amber color to it. The Karo syrup, notice I got light Karo syrup. When you buy Karo syrup, you can buy it as a light version or as a dark version. And in order to be able to see it easily, you really want to try to get the light version of the Karo syrup. So let me just do a little bit more here. I think we've almost got enough Karo syrup in the container. That's about right. All right, so there's Karo syrup. Okay, now if you look carefully, what we have already, the Karo syrup is floating on top of the honey. Now what that proves to you is that it's less dense than honey. If we want to find out if something floats or sinks, we compare it to what we're pouring it on top of. So here we have honey at the bottom. Believe me, if these two things were both water or both of the same density, they would just mix into one substance. But since this guy has a nice distinguished layer on top, then it basically proves that it's floating on top and has a less density than the honey that's below it. Now the next thing we want to do is go and work with regular old water, because as we go in order, this is going to have a slightly lower density than the Karo syrup, so it's going to float on that Karo syrup. But because the Karo syrup is clear and the water is also clear, if we pour it in there, it's going to be really hard to see the layers. So what we're going to do is get our water here in our little measuring cup, and let's put some food coloring in that just so we can see the different layers. So I'm going to choose green here, just so I don't have anything else green in this experiment. I'm going to put a couple of drops to make it nice and vibrant. Okay, and we'll just stir that around. So we have a nice deep green color, which will show up nicely against it. Now actually I don't want it to be quite that green. I want to be able to see through it nicely, so I'm going to add a little bit of additional water to it just to lighten that color up more than anything else. I'm not going to use all this water. I'm just doing that to make the green color a little bit lighter. All right, and so what we're going to do is pour it in. Now again, you got to be careful. You don't want to dump it in there because then it'll start mixing. It'll take a long time to settle out. So actually, if you have like a turkey baster or something where you can kind of like gently put it in, that would be even better. But in this case, we'll just gently pour it on top. And you should be able to see it start to form a layer right on top of that clear Karo syrup. And notice why we colored it green now, so we can actually see it very clearly. All right, that's good. So now we have three nice layers. We have our honey, we have our Karo syrup, and notice this nice green water that we've colored is floating right on top of the Karo syrup. If you gently tilt your bottle, you'll see all the layers move. So everything's floating on top. They're not mixing together. All right, next, we all know that oil likes to float on top of water. And so this is water, and here's oil. I'm not going to color the oil because we've colored the water. Everything will stand out. And again, we want to be careful. We don't want to go nuts. We want to just sort of gently pour it in there because we don't want too many bubbles to form. It's kind of inevitable whenever you deal with oil and water, you're going to get bubbling. But they will eventually go away. If you set this on the counter for an hour or so, then all of these bubbles will completely disappear. In fact, even over the next few minutes, they'll sort of disappear. So let's go ahead and put that in there. I think that's a pretty good layer, maybe a little bit more. Like this. Okay, so what we've shown here is oil is less dense than water because it's floating. That means for the same amount of the stuff, for the same volume of water, the oil actually weighs less, so that's why it floats. Now what we want to do next is we want to pour our alcohol, which is our rubbing alcohol, in there, and we're going to transfer it to a measuring cup so that we can have a nice pour spout and get it in there without getting it all over everything. Now what you can see after we poured the alcohol in is it kind of dove down deep and then it started to form these bubbles, and notice how it started to come back to the top. So you can clearly see that we have a red layer on the top. That's the alcohol that we colored red. So our 5 layers are, in order of increasing density, we have an alcohol layer, we have a an oil layer, and then we have the green water layer, and then we have Karo syrup, and then we have honey. And notice the boundaries are very, very distinct and very, differentiated from one another. Now notice, again, we have bubbles all throughout this container. If you were to let this sit on the counter for 30 or 40 minutes, these bubbles would basically all bubble up into their appropriate place and they would basically disappear. But what it shows you is this is your tower of density. It shows you that things can float on top of one another depending on their densities. And you kind of have intuitive understanding of that. Alcohol is real thin, it evaporates quickly and it just doesn't feel like there's much there. And then you have oil, which is a little bit thicker and heavier. And then you have water, which is even heavier. And then you have your syrups, like your Karo syrup and your honey. Now, if you notice carefully, what we see has happened is we have a nice red layer of alcohol here, but we also have kind of some of this red that's kind of bled down here near our water layer. Well, what's happened there is, what do you think food coloring is made of? Food coloring is some kind of coloring and it's mixed with water. When you squirt the food coloring out, it's mostly water. So the water in there, some of it has descended down and kind of mixed in with our water layer. So really, in our tower of density, we have honey, we have Karo syrup, and our water layer is right here. It's got the green stuff and it's got a little bit of red as well because that's some of the food coloring made its way down there. And then we have our oil, and then we have our red alcohol here as well. If we would have just put the alcohol in without it being red, without coloring it first, it would be a real difficult time to see that. All right, now we get to have a little bit of fun. Let's go ahead and put this on the white sheet of paper, and let's see if we can figure out what's going to happen to some of these things. So here is a rock. I imagine a rock's going to sink, but the question is, where is the rock going to stop? What layer is it going to stop at? Is it going to go all the way down to the water and kind of just go below that? Is it going to go all the way to the bottom? Or is it just going to stop somewhere in the middle? Let's find out. So if we gently drop this rock in, of course it's going to mix everything up along the way. Where is it going to stop? It made it through the water layer and it's gone into the honey layer. It looks like it's going to the very bottom. Okay, so this is our water layer here, which is kind of the greenish with this blackish stuff here. That's our water layer. So it looks like it made it all the way to the bottom. What does that mean? That means that that rock, the density of that rock is greater than honey. It means if you look at the same amount of honey that was occupied by the space of that rock and compare them together, the rock weighs more. And that's why the rock goes down there. And it kind of mixes things up along the way. Let's take a die. This is a regular old die that you get out of a board game. Let's gently drop it in and see where it goes. The dye goes through the alcohol, it goes through the oil, it goes through the water, it's into the Karo syrup, and let's just see if it settles on top of the honey or if it continues down to fall on top of the rock. And it looks like it's going into the honey on its way to the bottom of the container. Okay, so it looks like it's more dense than the honey. It looks like it's kind of wanting to stop, but it's going a little bit deeper. What about something like this pecan? This is something that everybody has handy. We'll drop pecan in. It's heavier than the alcohol, heavier than the oil, but as soon as the pecan gets to the water layer, which is this kind of blackish layer right here with the food coloring, it actually floats there. So that means basically whatever you drop in here, it's going to stop right at the point where it hits the liquid that it floats on top of. Pecans float on water because they're slightly less dense than water, and it sinks through these other layers in order to get there. Okay? What else do we have? Here is a piece of wood. Let's see what a piece of wood does. Piece of wood actually stays right in the top of the container. It doesn't actually go anywhere, it just stays right on top. So this wood is actually less dense than even the alcohol. Not even dense enough to go down any farther. Let's try this bottle cap. Actually, let's try this plastic cap. Just drop that in there and see where that goes. And I'll use my screw to actually kind of push it down, give it a little head start. And it looks like the bottle cap sinks past the alcohol layer but starts to float in the oil. So the bottle cap is floating on top of the oil. That means that the bottle cap is more dense than the alcohol, but not as dense as the oil. So it's less dense than the oil, so it floats there. The screw, I'm going to bet that it goes to the bottom. Let's check it out. It goes all the way straight to the bottom of the container. And you can see that right there. It goes straight to the bottom of the container. That kind of makes sense. What else do we have? And actually, it looks like the bottle cap descended a little bit farther. It was just really slow moving. It looks like it floats on top of the water. I have a red bean here. Drop the red bean in here. That goes through the water, and the red bean looks like it floats on top of the Karo syrup, at least for right now. So it went down through and it floats on top of the Karo syrup. What about a straw? Regular old straw, like a drinking straw. Looks like it goes through the alcohol layer, and at least for now, it looks like it is right on top of the oil. Anyway, you can have fun dropping various things in there. I have a paper clip here. Let's see where the paper clip goes. Paper clip shoots down, goes into the Karo syrup. Let's see if the paper clip stops on top of the honey or not. Let me turn that here like this. Looks like the paper clip might stop on top of the honey there. It just depends. Sometimes whenever it hits the really thick layers, it just takes time to settle through. So that is what we call a tower of density, or a density tower. Basically what we're doing is finding different liquids from around the house and choosing them and stacking them on top of each other so we can see the different layers, and that's telling us how dense each of these liquids basically are. The least density item, liquid's going to be at the top, and the most dense is going to be at the bottom. Once you've constructed your density tower, you can start dropping various things around the house. You know, make sure you choose things you don't mind if they get a little wet or a little sticky. And depending on how dense they are, that's where they're going to stop and start to float. So they'll go down to the level, to the liquid level where they begin to float. And it all depends on the relative density. I'm Jason with scienceandmath.com. I hope you've enjoyed this experiment. It's very simple to do, very easy to find materials. Just need to make sure and get permission before you start mixing things together to make sure it's all safe, which this all is. And then you can go have fun learning about density, learning about buoyancy, and using the knowledge of science to predict how this sort of thing is going to work. Learn anything at mathandscience.com. Today what we're going to do is show how air pressure that's all around us can actually hold the water inside of a glass in place, even when the glass is turned upside down. And so we'll have a few things that we'll explain along the way, but that's basically the bottom line. All you'll need for this experiment is an empty glass that you're going to use to actually perform the experiment. You need another glass of water or just a sink, to actually give yourself some water to use. And then you'll need a piece of cardboard. Now this is nothing special. This cardboard just came off of something I found in the pantry. Just cut it out to be slightly bigger than the cup that you plan to use. Now here in the studio I have a basin to catch any water that drips, but you can just use this, do this experiment either in the tub or just in the kitchen sink, works just fine as well. So basically what we're going to do is we're going to put our empty glass inside the container, and then what we're going to do is we're going to put some water inside of it. So let's go ahead and put some water, and we're going to fill it up most of the way. I mean, you can actually do this experiment by filling it all the way up to the brim with water, and that works fine. It's just a little bit harder to actually perform if you do it that way, but it'll work either way. As long as you don't have an enormous glass of water, it should work fine either way. So the next thing we're going to do is we're going to put this cardboard down on top of the rim of the glass. And then after we do that, we're going to reach down and pick the whole assembly up, flip the whole assembly over so that the water is pushing and gravity is pushing it against this piece of cardboard. But we should find, if we do everything correctly, that the water actually doesn't fall out of the glass at all. So let's do that. We'll just put it right on top, just like this. Okay. And we're going to push down on it, and then we're going to lift up the whole thing like this, and then we'll let it go. And you'll see that everything is in place, that the water is inside of the glass, the cardboard's getting wet, it'll probably fall just like it did just there after a minute, but you can see that everything was held in place for a good long amount of time. By the way, the only reason that it fell was because the cardboard got wet. If you get cardboard wet enough, it's going to lose its strength. But for a good few seconds, you can see that it was held in place seemingly just by a little piece of cardboard. Now we can actually try to do the whole thing again, but instead of using cardboard, we can use a piece of plastic and see if that changes anything. So let's go ahead and fill everything up to the top here, all the way to the brim with water like this. And then what we'll do here is we'll just use a blue paper plate here and just see if we can get it to work. So let's go ahead and push down right on top, flip the whole thing over, and then let go. And we'll see that everything is held in place And actually the plastic plate works a little bit better because it doesn't get soggy. Whenever cardboard gets soggy, it's going to fail. What's happening here is we have the water inside, and it is pushing down on this guy, and it is definitely wanting to get out. But you have atmospheric pressure out here, and that means you have air pressure. The pressure and the pushing of the air around you is actually pushing up from underneath onto this plate. And it's a really great demonstration to show you how strong air pressure is, that it's strong enough to hold. I mean, this glass of water is pretty heavy, you know, but it's strong enough to push against this plate and to keep the water in place. So it's basically an experiment in balancing air pressure. You have air pressure pushing up from the outside, you have water that the force of gravity is pushing down from the inside. Clearly the water is staying inside the cup, so the pressure and the force outside the cup must be greater than what is the weight of the water inside, and that's why it's able to be held up. So again, you can do this with a piece of cardboard. It works for a few seconds usually, but then it'll usually give way. If you find some piece of plastic, it works, you know, even indefinitely. Now I'm going to start shaking it a little bit, see how strong this is, but it will probably give way in just a second. So I'm going to start doing this. You can see this is actually, there it goes, finally gives way. So just a little bit, when one of the corners just lifts up just a little bit and lets some of that air start pushing in, then the water starts gushing out and then the whole thing collapses. So it's a great little experiment, takes just a few items from around the house, takes 5 minutes, and it's a great way to learn about the fact that we have all this air around us and it's pushing on us with air pressure.
Learn anything at mathandscience.com.
Today we're going to build a very simple matchstick speedboat, so to speak, and it's very simple to do, and you just use the materials that you find around the house, and we'll learn about surface tension of water along the way. And so what you'll need for this experiment is a matchstick. This is going to be your boat. You'll need a Q-tip. You'll need some sort of plate or bowl to hold everything in. Now the pepper I'll explain later. We'll do that sort of as a part B to the experiment, so you'll need that a little bit later. You'll need dish soap. Dawn seems to work the best, but other soaps probably work just great as well. And you'll need some sort of water. Here I have a glass of water, but you could use sink water, tap water, bottled water, whatever. So let me take the pepper and just kind of move it off to the side, because that's not really for now, that's for later. And what we'll do is we'll put everything right in the middle here so you can see everything. We'll take everything out, so we'll put our safety glasses on. Now we're not going to actually light this match, but just with any of these experiments, just go ahead and make sure you have permission to use everything here. If you need to go ahead and ask, go ahead and ask. So what we're going to do is pour some water into this plate. How much water we pour doesn't really matter. You just want to have enough to float a matchstick. Now let's give it a few seconds to simmer down. Now what you may or may not know about water is very fascinating actually. Water is a special kind of molecule. And for those of you who want to know, it's called a polar molecule. And what that means is that the way the water molecule is constructed, whenever water bumps up against air, in other words, at the interface of the top of the water, where you have water at the top and then you have air above it, the water likes to form a skin, so to speak. And you can sort of see that when you I can just do it with my finger here. When you just put your finger barely in the water, you can sort of see that skin just kind of like raise up above and kind of touch your skin. And so we say that almost like the water has sort of like a skin or a surface. And that surface is called surface tension. Tension meaning because it's kind of tight, surface because it's the top of the water, so surface tension. In fact, if you look in a river or a pond, you'll see bugs can actually crawl and walk on top of the surface tension. So basically, because of the way the water molecule is formed, because it's a polar molecule, that means that whenever it comes in contact with the air, it likes to kind of contract and form this sort of skin around it that, is sort of like at the very top layer of the water. And what that means is that you can take very light objects and balance them and float them right on top of the skin. So just drop your little matchstick in there and you can see that it's right on top of that surface tension. It's right on top floating in the water. Now, everything is motionless. That's why I wanted to give the water a chance to simmer down. And we'll put a little bit of Dawn dish soap onto a Q-tip, like what we're doing here. So you just want to put a little bit. You don't want a lot. You don't need a lot. Just a little bit, just enough to make it blue. That's another reason to use Dawn soap, because it's nice and blue and you can see what you're doing. Okay, so here I have a Q-tip with blue soap, and I have my Matchstick speedboat, kind of resting in the water. So at the end of the speedboat, right at the end here, you want to touch the water and watch what happens to the matchstick. 3, 2, 1, touch it. Look at that. And it left behind. And you can kind of chase it around, at least for a little bit. You can kind of chase it around and you can see that it moves. Now, just to kind of show you for comparison, if I use the other end of the Q-tip and touch it, nothing happens, right? Nothing happens. It's only when this soapy end touches it, does it like to move away, right? So we call it a speedboat because you have this guy floating in the water and you can watch it zoom across. Now, why do you think that happens? Well, it happens because the dish soap is basically built to disrupt surface tension. It helps to release the oils and the fats and things like that that are caked onto your dishes when you're trying to wash your dishes. So the soap is basically built to disrupt the surface tension. So if you have something floating on top of the surface tension and then you disrupt it from behind, then what's going to happen is the water is going to kind of ripple through, and that surface tension is going to be disrupted, that skin is going to be disrupted, and it's going to kind of ripple through the water, and it's going to carry that speedboat, the matchstick, so to speak, with it. So it's kind of an interesting thing to show yourself what surface tension is, to show you that dish soap really can disrupt that surface tension and it carries away whatever's floating on the surface with it. So what we're going to do now is clean this water out, get all the soap out of it, do the experiment again, and we'll do it with some black pepper and you'll be able to see the effect, I think, even a little bit easier. So let's go ahead and do it again, and this time we'll, instead of a matchstick, we'll actually put some pepper flakes on top and you'll be able to see something neat there. So let's go ahead and put a nice fair amount of water in there, same as before. Now in this case, we will use some pepper. Now it doesn't have to be cracked pepper, you can just use whatever you have. So let me go ahead and just kind of be vigorous about it. We'll just kind of grind this in there. You want to put a lot of it in there to really see the effect really well. So I'm going to kind of go a little nuts here. Okay, that's good. Just so that it kind of coats the whole surface and you can see everything. Now, based on what happened before, what do you think is going to happen this time? Well, before we said when we put dish soap in water, it disrupts that surface tension. And what that means is the skin that's formed is broken down. And so it kind of propagates out from the point that you put the soap in there, it kind of spreads out. So if we put soap in the middle, we should expect to see all of this pepper kind of move to the edges. So let's see if that's what happens. So we want to go ahead and put a good chunk of soap there, but not too much. You don't want to go nuts with the soap there. And you want to put it right in the center. 3, 2, 1, insert. Now you can see the pepper just goes straight to the edge of the plate. Notice it goes all in a circle. Everything is in the circle just kind of moves out. Now if you try to keep doing it, it does work a little bit, but not nearly as much as it did the first time. That's because once we have soap in the water, the surface tension is basically disrupted. And you can't keep putting soap in there and expecting the same thing to happen, because once the surface tension is broken down, it's done, it's gone, it's not there anymore. So once it's done sort of like one time, then you have to sort of reset to do it again. So if you want to do this experiment again, you need to empty the plate, wash it out, clean it out nicely, and then start over, because once you have any soap in there, it kind of prevents it from happening again. So again, we learned about surface tension. That's the skin on top of a liquid, especially water. When it comes into contact with the air, the way the water molecules are built, they like to kind of cram together and form this skin on the top. When you put soap in there, they get inside those, in between those molecules, and break that down so that that skin doesn't like to form anymore. So you can see it propagate out from wherever you put your soap. So in the center, it all propagates out to the edges. Of course, when we use our speedboat, it kind of pushes that little speedboat along. It's a very, very simple thing to do. Almost everybody has these materials at home, and you can learn about some real science along the way. So go grab an adult, go grab these materials, and have fun doing this experiment and learning about surface tension.
Learn anything at mathandscience.com.